That's incredible. Your first babysitter? Your first babysitter?
Are you guys going to stay? You want to leave? That's okay. I understand. This is going to be fun.
We'll play.
I don't know what all these people are doing.
We'll play for like half an hour for
Okay, cool. Yeah, I can't. After I have to get grilled, but you should like mingle with the family. You've met my brother.
Yeah.
You know, the one that looks the same as me. And then my aunt Barb is really friends. Thank you.
You got it.
Good to see you.
You just got two blue.
I'm a little confused.
Good to see you.
Yeah. Let's go to oxygen bar. Yeah, but that's for me. You're gonna shake my hand or give me You want to go to the oxygen bar with me?
He's in here working hard.
No problem. You sound like me.
It's like got a typical head cold, but it's terrible. It's ricocheting like across the town. By the time it gets to the first person, he's to reinfect.
Nothing like a mutate to reinfect.
Oh, God. So, yeah, I have a head cold for like weeks.
Do you guys have a coach?
Yeah.
Is that Adelaide on Skype?
Hi, Adelaide.
I was told Adelaide would be here.
Oh, is that us?
That's
Yeah,
it.
that is us.
Instructed to that Adelaide forum.
Yeah.
Hello, Adelaide.
Hey, Adelaide.
Is she actually in the little window down there? I
No.
signed.
I didn't see her. Don't let me go.
Is this Adelaide?
No, I don't know if there's anybody can see. It's just like one way.
I got a text saying she's watching it. Hi. Good. How are you?
Getting closer. So you're coming back from the West Coast?
It's gonna feel nicer for her though. We already know it.
How much was that shirt?
How are you doing?
Staying very busy.
Yeah.
Yeah.
Hold up.
You just had first birthday. Yeah. More of a milestone for
I'm just webcamming it, which is very suboptimal. But
Oh yeah.
yeah, it's possible. I haven't. Well, I think there's somehow. Oh yeah, there's 3 viewers, so probably. Yeah, she's probably. Adelaide, if you're there, hello.
So, I said, I'll just make the column really huge and see what.
All right. So it was intentional.
Yeah.
Okay.
So like a last ditch effort after trying to do everything I that I thought worked, but just keep getting out there.
I mean, you worked around it. Right,
Well,
so
we're
we
not
can
out of the
sit
woods
down here.
yet.
Yeah. No, we didn't sit here. I think we're being shut down. Make sure and blocked
You would be closer to that.
Next question.
Protect the face. I'm Holly home. I threw a big tantrum about it because I think I canceled all of it, so I
I think we do. I can only see that there's like 3 viewers, so I can only see that there's like 3 or 4
Hi.
viewers, but
Thanks for watching.
no, I think it'll be fun.
Okay.
Yeah. Sorry, I'll move this. Here, can you put it like up against the wall? Yeah, that is it. Julie, is it distracting to have this? Like, I can like make the screen black. Like, is it distracting? Okay.
If we sit here, will we block the view?
I think so.
We'll sit adjacent.
Yeah, that's great.
Video presentation.
Yeah.
You know what? There's those were 2 seats I think.
Oh yeah. Do you want me to grab your stuff?
This is actually the like video.
So I shouldn't sit.
So if you could sit over there, that'd be great.
Go in the middle. Go in the middle. This is gonna go on YouTube.
Yep. Although it may not be available afterwards. I don't think I'm recording it. It's just available right now, like live. Yeah.
Good morning.
Good morning.
Outstanding. I love that. I'm Chris Edwards. I'm Julie's advisor. I'm going to get things rolling. Pardon the voice. I've got a cold, and I will likely be here. I will affect you all. I'm not going to stay away from you. But it seemed like there was something kind of important happening. So the idea is saying, no, I don't think so. So Julie has done some really interesting work on a hard problem. This problem of ringing in IC engines and how to deal with high-load homogeneous charge. It's a tough one in terms of structuring the problem and understanding it, and then developing the tools that you need to investigate that. And that's the problem that Julie has tackled. She's made some really good headway on that. I first met Julie before she was a Stanford student. I think it was like a fellowship interview day or something of that sort. And thinking back about this, my impression was that she was very serious. not that look at all. Her face, but very not poker face, but serious. And a little dour. I was thinking, wow, this is an intense person, but very charming and capable, and done lots of good things. Then she came to Stanford. It was one of my advisees, and we would have conversations about something. She looked so serious. I tend to be kind of a smiling kind of guy. I don't know what I look like today because I don't feel well. But I tend to be kind of that way. Thinking, wow, she's so serious. I wonder if she's having a good time or not. Then I had her in class, and she always just looked so serious. And it was funny because I think she's interested in the energy systems, the kind of stuff that I do, and the rest. But I was kind of getting a little worried that maybe this wasn't a really good fit for her. So finally, one day I sat her down and I said, I'm just kind of worried about you. I know you want to do something, but I'm concerned that it won't be a good fit because you just don't look like you're having a good time. You look like you're unhappy. And she finally looked at me and said, I'm unhappy because you won't let me into the research group. I into the research group because you look unhappy. At that point, she pretty much smiled the way that she's been that way ever since. I really love working with Julie. I love the way she attacks problems. I love her value system and the way that she brings that to bear and everything that she does, which I think is really special. Those of you who've been around probably know that I refer to her as Badger. That probably makes some people uncomfortable. I've completely forgotten about it. The name Badger is completely interchangeable with Julie. But you may not realize why I call her Badger. You probably think that it's just a matter of coming from Wisconsin and the Wisconsin Badgers, and there's a certain football-esque thing to this. But if I play the football side out, it's more like Marshawn Lynch and what they call beast mode. She has Badger mode. So periodically, when something is getting in the way of Julie, and she's annoyed, it's a vendor, it's somebody who's overdue with a part or something, she goes into Badger mode. The difference between her and Marshawn Lynch, when she goes into Badger mode, he goes into beast mode, is he just runs people down. In her case, she does it, but she might do it by baking cookies, calling them 6 times a day. She just has her own way of doing it, but she is going to get the result that she wants. And in my way of thinking, she has gotten the result that she wants out of her PhD, and I'm very proud of her.
Thanks, Chris. That was too kind. I'm Julie, and today I'm going to tell you some of the things that I did during the course of my PhD here at Stanford, advised by Chris Edwards. The title of my talk is Experimental and Numerical Tools to Investigate Rigging in Internal Combustion Engines. And if that doesn't make sense to you, I hope at least by the end of the talk you understand what the title meant. A fitting title. And I forgot to thank you all for being here. There's a lot of you. I'm excited. So I want to start by taking a broader view of transportation vehicles globally. So to get a sense of scale and kind of projections of where we're going. So in 2012, there are 75 million new passenger vehicles added to the world's roads. And that's as if 9 New York cities worth of people were buying a car for the first time. So big scale, lots of vehicles being added. And so the scale of that indicates that any efficiency improvement or improvement in emissions that we make will have an impact over the number of vehicles and then also be integrated over the lifetime that those vehicles will be on the road, 10 to 20 years or so. So the International Energy Agency puts together something every year called the Energy Technology Perspectives Report. And one of the things they do in that report is they detail what technology would need to come online at what time scale to achieve a certain goal in terms of carbon mitigation. And so they have something called the 2-degree Celsius scenario, and they detail in this graph, it's showing for transportation, passenger vehicles, what the projection would have to be to arrive at the 2-degree scenario, which is considered a fairly ambitious but achievable scenario. So on the y-axis, we have vehicles, millions of vehicles that are being added, and on the x-axis, we have the year. And so what we can see, okay, you can see this gray bar is represents gasoline vehicles, like what we all drive. And we see that demand will continue to increase slowly in time, and until about 2020, the number of gasoline vehicles on the road will continue to increase. And after that, they'll decrease to be replaced by more efficient transportation architectures. But one thing I really want to point out about this is that I've bracketed here all of the categories that are combustion-based transportation systems. So these are more efficient than the gasoline vehicles we drive today, but they still rely on an efficient combustion process, either in the form of a hybrid or a plug-in hybrid or a very efficient diesel engine. And so that means that although electric vehicles are good, research is still very much needed in the area of combustion engines to achieve these kinds of aggressive targets for efficiency. So next I want to tie in the relationship between emissions and efficiency. So on this plot, the y-axis is work-specific exergy consumption, which is an inverse efficiency type of metric. It's how much fuel resource exergy put in to get 1 unit of work out. And on the x-axis, we have work-specific carbon emission to the atmosphere. So how much carbon was emitted per amount of work that we produce with the engine. And we see that each fuel that we choose forms a straight line on this graph based on its exergy to carbon ratio. And so what we want is to be down in this corner with higher efficiency and lower carbon emissions. So on each line, the goal, so let's say we're using gasoline, we would be trying to move down this line. And we could also emit less carbon by switching using the same combustion strategy, because this is spark ignition engine, moving to a fuel with less carbon intensity. So based on your fuel, emissions and efficiency are directly tied. So my motivation is to improve the efficiency of internal combustion engines by identifying barriers to increasing the efficiency and then developing tools to understand those barriers and overcome them. So the outline of what I'll take you through today is an overview of internal combustion engines, and then I'll talk specifically about ringing, which is the particular barrier to efficiency that I'm focused on in my work. I'm going to talk about some numerical modeling to model the ringing phenomenon and some results of that. And then finally, I'll talk about an experiment that I designed and built. So let's dive right into engines. Captive audience. Secretly, I always want to just talk about engines, and now you have to. All right. So in an internal combustion engine, we take air and fuel, and our goal is to make it work. We do that by a cyclic process of compression, combustion, work extraction, and then gas exchange. And so what we see here in the first panel, this is an air-fuel mixture in a piston cylinder, and the piston is at the bottom, called bottom dead center. So the first thing we do going from 1 to 2 is a compression process. Piston comes up, the volume gets smaller, and the air-fuel mixture is at a higher pressure. Then from 2 to 3 is a combustion process where the chemical bond energy of the fuel is converted into sensible energy, and there's a mixture of combustion products, so that's represented by yellow. And this is at approximately a constant volume. And moving from 3 to 4, the piston moves back down, extracts work, and then to cycle back from 4 to 1, the exhaust valve will open, and the piston will move up to expel the spent air-fuel mixture, and the intake valve will open to draw in a fresh charge of air and fuel. So we'll cycle around like that. And another way to visualize this process is on what's called a pressure volume plot. So on the y-axis, we have pressure inside of the combustion chamber, and on the x-axis, we have volume. So as the piston moves from bottom to top, we're moving from large volume to small volume. So that represents the two extremes here on the x-axis. So we begin with down here, and this is the compression stroke, moving from large volume to small volume and an increase in pressure. The combustion process takes place here, going at approximately a constant volume to a higher pressure. And then the expansion stroke is at a higher pressure than the compression stroke and comes back to that original volume. And the area enclosed by this loop is the work that the cycle produces. So for a given amount of fuel that we put into the engine, we want to maximize the area of this work loop to get a higher efficiency. So this, the combustion process can be accomplished in two ways traditionally. The first is with spark ignition. So most of us drive spark ignited gasoline vehicles. So in a spark ignited engine, the air fuel mixture is compressed and then it's ignited with a spark plug, and a flame front propagates out from that ignition source throughout the mixture to convert it all to combustion products. And one of the drawbacks of the spark ignited engine strategy is that it's limited in its compression ratio by the propensity of the air fuel mixture to knock. And higher compression ratio translates to higher efficiency, generally speaking. So there's a limit on the compression ratio for these engines. The other traditional combustion strategy is diesel combustion. And in a diesel engine, instead of compressing the air and fuel, just air is compressed in the cylinder, and then near the point of minimum volume, a high pressure injection of fuel enters the combustion chamber, and as that fuel mixes with air, it reacts. So diesel engines are not limited in compression ratio by knock, but they do have the consequence of fuel-rich and fuel-lean regions in the cylinder tend to produce soot. It's hard for the air and fuel to all find each other when they weren't pre-mixed. So diesel engines are often limited by soot formation. The type of combustion that I want to talk about today and that I've studied in my research is called homogeneous charge compression ignition, or HCCI. And an HCCI engine is trying to bring together the benefits of the two traditional combustion strategies I talked about and try and also mitigate some of the drawbacks. So in an HCCI engine, an air, fuel, exhaust gas mixture is pre-mixed and is compressed to a higher compression ratio than a spark ignited engine. And it's compressed all the way to the point that it's at a high enough temperature that the mixture begins to auto-ignite. So there's no ignition source, there's no actuator triggering when the combustion will begin. It's based on the chemical kinetic rates of that auto-ignited combustion process. And so you can imagine if you don't have a trigger, then the initial conditions will matter a lot for this type of combustion process. And the reactions occur throughout the cylinder whenever the chemical kinetics dictate. So some of the advantages and disadvantages of HCCI. HCCI has a higher efficiency than a spark ignited engine because it operates at a higher compression ratio and it has a square PV loop. So on that pressure volume plot that I showed, some of the corners are more filled out and it has a larger area for the amount of fuel that you put in. It also has reduced heat transfer losses, which are one of the largest sources of inefficiency in IC engines. It has additional benefits in terms of emissions. Because the air and fuel are premixed, the HCCI combustion process doesn't emit soot from the engine. And it also operates at a lower peak temperature than either gasoline or diesel engines. And this has benefits in terms of producing less nitric oxide. Some of the challenges associated with an HCCI combustion process are that because it's kinetically triggered, it's difficult to control. So whenever during the compression process the air and fuel reach their auto-ignition state, the combustion will occur. And also, because you can't necessarily trigger and predict how every cycle will behave, if one cycle doesn't behave the way you expect, that exhaust gas is mixed with the following cycle and it can introduce a cycle-to-cycle coupling. So sort of a misfire in one cycle will have consequences for the following cycles. And also the exhaust gas mixed in to the cylinder displaces air and fuel, causing this type of combustion strategy to have lower power density. And what that means is that if you had a certain power requirement for your engine or for your car, you would need a larger sized engine running an HCCI combustion strategy than a spark ignited combustion strategy to produce the same amount of power, even though it was more efficient. And this has implications in terms of material cost and weight of the vehicle. And so you might ask, why not just get rid of the exhaust gas and just mix the air and fuel and compress them? And that's a good idea. But there's a limit on the amount of, there's a limit on how little exhaust gas we can use, and that is limited by this phenomenon called ringing, which I'll discuss today. So ringing is a barrier to internal combustion engine efficiency. And what ringing looks like is, it looks like these little pressure waves on a pressure trace. So the panel on the left is a pressure trace in an engine. It's a pressure versus time or versus crank angle degree, crank angle being the position of the crankshaft during the cycle. And so you can see we have our same compression process, combustion, and expansion stroke here. And this is a nice smooth HCCI pressure trace. And the trace on the right exhibits these little fluctuations in pressure. And those can cause damage to the engine. And these are termed ringing, because it's an oscillation in the pressure. So ringing occurs when that auto-ignited combustion process produces pressure waves, which reverse the engine and then can cause thermal damage. So what does that damage look like? We see here a piston that has evidence of some thermal heating or erosion. And that results from, if the pressure waves are strong enough, they can scrub away the protective thermal boundary layer over the piston, causing the heat transfer rates to be very high, and that can damage and erode material. Ringing can also produce very high local pressures, which can cause damage to piston rings. So thinking about scrubbing the boundary layer off, in terms of a practical example is, even if it's the same temperature outside, you feel colder when it's windy because the wind is scrubbing away the nice blanket of warm air that you warmed up around yourself. All right, so how do those waves form? We know they're bad, we know they're good. How do they form? How can we understand them to begin to alleviate the problem? So we know that in that mixture of air, fuel, and exhaust gas, there are fluctuations in temperature on the order of 10 to 100 Kelvin. So some regions will be warmer and some regions will be cooler. And since the timing of the combustion is determined by the chemical kinetics, this is very important. The hottest mixtures, or the hottest regions, will tend to react ahead of colder ones. So what we can think about is, let's imagine that this was the hottest region in the cylinder, the place with the shortest ignition delay time and the most ready to react. And the initial reactions cause the gas to dilate. And what can happen, normally you think of an explosion and things go outward. But what can happen is if the mixture was energy dense enough, that dilation can be limited at the boundaries of the reacting region by the local sound speed. So molecules can't move faster than the speed of sound, and so this expansion will be impeded by the sound speed, and a pressure, an overpressure will develop behind this wave. So you can think of this region having higher pressure and a reaction zone here, and this overpressure is traveling outward into the unburned mixture of air and fuel. And what can happen is when that pressure wave encounters the next neighboring region of air and fuel, it will compress that region, which can prompt that to ignite and strengthen the dilatation. So a pressure wave can build and prompt further reaction and then be reinforced, and this coupling can occur. And that's called a developing detonation. So the important point here is that the reaction zone and a pressure wave become coupled and mutually reinforcing. And this can produce pressures that are higher than you would expect to see based on the amount of air and fuel we put in the engine. I want to take a tiny step back and talk about why ringing is a good problem to try and solve in terms of why this is a promising thing to be chasing after. There was some previous research done in our lab some experiments by a student named Matt Sverchek. And Matt was trying to do very efficient combustion at high compression ratio. And so he had an experiment that could go to high compression ratio, and he was auto-igniting stoichiometric methane and air with no exhaust gas dilution. And he phased the combustion to occur at the point of minimum volume in 2 ways. So because the compression ratio was so high, he needed to have a way to prevent the mixture from reaching its auto-emission temperature before the point of minimum volume. So he did this in 2 ways. The first is he just cooled the overall mixture down before the compression process, and then it would arrive at that temperature later. And that's what we see in the gray pressure trace here. We see the compression, and right here the auto-emission occurs. And we see these very sharp, strong rating pressure waves. And then the other approach that Matt used was water injection. He injected just a little bit of water into the cylinder during the compression process, and the water vaporized, cooling the mixture while it was compressed, and that allowed it to reach its auto-emission point at the point of minimum volume. And what we see from that trace is that this is a very smooth pressure trace that doesn't have evidence of ringing. So this was not, I don't think, something that Professor Edwards expected. It wasn't something that Matt expected or I expected. And this is promising because there is a result that demonstrates ringing can be disrupted. So one more thing I want to point out is, like I said before, the concept of the highest pressure we would expect to see in a mixture based on the amount of air and fuel and the compression ratio. We'll call that the constant volume pressure. And what that means is the pre-combustion state, which is indicated by the arrow here. If you took the chemical reactions to equilibrium in a constant volume adiabatic vessel, the constant volume pressure is the pressure that would be reached, and that's indicated by this red line here. So if this is the maximum pressure we would expect to see based on what we put in, what's happening up there. So that is evidence of the gas dynamic coupling that we talked about, of a pressure way of compressing things before they react, causing them to reach even higher pressures than they would have. And so, yeah, we see almost 400 bar pressure higher because this wave reached it. And so that's as if some of the mixture experienced a much, much higher compression ratio than actually the motion of the piston would have imposed. So the question going forward from this is, how do pressure waves interact with a large scale inhomogeneity, such as water injection in the engine? And when I say large scale, I mean larger than the scale of the temperature fluctuations that I talked about earlier. So how can we find out what was happening in the water injected case that made it so different? So the sensors that we have in the engine that gave us that data are a pressure transducer. We can think of this as the cylinder, and we can think of this as the combustion process happening. And we have a pressure transducer mounted in the wall of the chamber, and that gives us data at one point in space located on the wall. But the things that we're talking about might be taking place in the center, and also will have some sort of spatial component as gases dilate and they couple. So the pressure transducer is an incomplete source of information about this gas dynamic coupling and the autogenetic combustion process that produces ringing. Another thing we can do to try and understand this phenomenon is to use a numerical model. So we can think about modeling the essential physics during the autoignited combustion process and determine what types of conditions give rise to ringing and which types don't, or when do we see the gas dynamic coupling and when don't we. And so we can feed into the model different initial conditions. So we can imagine, say, this is maybe the concentration of water in the cylinder, maybe there's more in the center, and maybe this is the temperature profile, and we can feed those initial conditions to the model and see whether the gas dynamic coupling occurs. And this can be used both to interpret experiments, and then also to target questions that we would want to try in future experiments. And a final way to get spatially resolved information in the center of the combustion chamber is through optical access. So an optical access engine allows us to actually take data and see where the combustion process is happening in the cylinder visually. And then if we also employ a technique called Schlerin imaging, we'll be able to see where the density gradients are and be able to see pressure waves and then also reaction fronts. So the luminosity will indicate where the reaction is happening, the Schlerin will indicate where there's pressure inequality and where there's a wave. And we can see whether there's coupling or not. All right, so now I'm going to explain the numerical model and some of the results of that model. So the model that I wrote is a quasi one-dimensional reacting compressible flow model. That means it captures one dimension in space and also dimension in variation in time. The equations that are relevant for this flow regime are the Euler equations. They're the conservation of mass, momentum, energy, and species. And for each chemical species, there is a different species conservation equation. So depending on your chemical mechanism, that will determine how many equations you have. So I'm using the GRI 3.0 mechanism for methane. So I have 53 equations for that. The model neglects viscosity because viscous terms are negligibly small in this flow regime. And I'm neglecting diffusive transport because those processes are much slower than the time scale of the combustion effects that I'm studying. The spatial derivatives are calculated using an essentially non-oscillatory or thinner scheme in space, and I'm using Cantera for thermodynamic properties. Cantera is using the GRI 3.0 mechanism for the chemical kinetics, and the stiff system for the chemical kinetic equations is integrated using a numerical package called CVODE. So the first model result that I want to share is sort of a case of idealized HCCI where there's very little variation in temperature. So in the results that I'll show, we'll see pressure and mass fractions of different important species. So methane being the fuel, the oxidizer, and water being one of the combustion products. And we'll see how these things evolve in time. And you can imagine this kind of like if you were to drop a stone in a pond right here, you would see ripples emanating from the left side. So in all of the cases that I'll show, the left side of the plot is the spot with the highest temperature, and so that's where the combustion will begin. And there will be different chemical compositions or different gradients of temperature coming from that warmness point. So in this case, there's a very shallow temperature gradient of 0.01 Kelvin per millimeter coming out from here and decreasing. And the last feature I need to point out before I show you a result is the constant volume pressure is indicated on each of these plots with the light blue dashed line. So keep in mind that is the highest pressure you would expect to see in the absence of any gas dynamic coupling effects. So we see after an initial ignition delay time, I've paused it here to talk about it. We see that the fuel is being consumed as the combustion process proceeds from left to right. The oxygen is being consumed, water is being formed, and the pressure is increasing. And it's increasing right up to that 132 bar that we would expect to see. So in this case, there's not evidence of coupling because there's not an overpressure developing. And so we see, if I continue playing video, that we arrive at the constant volume pressure and that all of the air and fuel have been converted into products of combustion. But this is a somewhat unrealistic scenario because we know that the temperature fluctuations in HCCI engines are larger than this. So what I'll show next is an example with a more modest temperature gradient of 1 Kelvin per millimeter. And so everything else about the mixture is the same, but the temperature gradient is steeper. And what we see, the ignition begins over here, and we can already see this overpressure developing. And you can see that the reaction front is coupled, or at least co-located with the pressure front. And already, even though only a little bit of the fuel has been consumed, the pressure is approaching the constant volume pressure. So if I play it further, we see that this gas dynamic coupling produced pressures nearly twice the constant volume pressure. And the reaction front was reinforcing the pressure wave, and the pressure wave was prompting further reaction. And I also want to point out that if there was a pressure transducer in this wall right here, it would still not have registered the combustion process. And so that's sort of reinforcing the idea that this is a more complete way to think about this type of a problem with a spatially resolved aspect to it. So I'll play that one more time. You can see how it couples rapidly and then it propagates outward. So factors that affect this gas dynamic coupling. The first, as we just saw, are temperature gradients. The initial conditions and the initial temperature gradients present in the mixture can determine the outcome of the propagating combustion wave and the mode of that wave. Also, we know that operating an HCCI engine with exhaust gas tends to prevent rain. So we know that the overall chemical composition in the mixture will play a role in whether rain occurs and when it doesn't. And then finally, from the water injected data that Matt took, we know that local chemical composition might have an effect because it's likely that the water stayed localized in the center of the combustion chamber. So we'll also see a case where the chemical composition is not uniform. So the first case that I looked at to think about dilution, uniform dilution, and a changing of the overall chemical composition is to dilute the mixture with an inert gas like argon. So instead of jumping right in with a realistic exhaust gas composition, I wanted to separate this into sort of more methodical test cases. So argon is an inert gas, and this is a mixture that's diluted 20% argon by mole. And what we can see is the combustion process began here, but this looks a little bit different than the previous case. We see that the pressure wave is more rounded and it's out ahead of the reaction zone. So dilution with just 20% argon did prevent the initial gas dynamic coupling that we saw when we didn't have the argon. But what we see if we continue to let the wave evolve is that the pressure wave and the reaction front coalesce and couple and produce this high peak pressure. And so while the argon was able to delay the coupling, it didn't fully disrupt the coupling. So a logical next case to look at would be dilution with another inert gas with a higher specific heat, like nitrogen. So everything about this case is the same as the last case, except the inert gas is nitrogen. And so what we see when we look at the simulation is that the initial coupling did not occur because the nitrogen was able to disrupt it. And you see the reaction front is here, the pressure wave is out in front of it, and they're not located in the same place. But if we continue to play the simulation, we see that the reflected pressure wave off of the wall, once it passed through the reaction zone, it prompted coupling to occur. And so we see that that propagated in the direction where there was still air and fuel that could be burned. And that's why it propagated in this direction. So while nitrogen could disrupt the initial coupling. It couldn't actually prevent this sort of secondary coupling effect that we saw. And so if it weren't a reflected pressure wave, we could have imagined another region of the cylinder reacting and launching a pressure wave that could prompt coupling in another region of the cylinder. And so this type of behavior from the model provides further motivation to look at this type of thing experimentally, when you won't have, in a real engine, you won't have such a simplified case. So the final result that I want to share today is a result showing spatial segregation of different chemical species. So on the left, there is air and fuel with no dilution. That is similar to the very first strong coupling case that we saw. And on the right is pure water vapor. And so what we'll see is we'll expect that initial gas dynamic coupling, and then we'll see what happens when the wave encounters a region of water. And so what we see is that once the pressure wave doesn't have the reaction to be reinforcing it, it loses amplitude very rapidly. And this is an unrealistic amount of water to put in an engine to achieve the kind of high power density that we're trying to pursue. But it's a very helpful way to think about how a region that was water rich could affect the coupling. So next I'll talk about the experiment that I designed. All right, so the experiment is called a Bowditch optical access engine, and it's named after Fred Bowditch, who came up with the idea. And a Bowditch engine allows us to get spatially resolved data about the combustion process, whereas the pressure transducer only gives us one point in space. And if we employ Schlieren imaging, we can also see the density gradients. So we'd be able to see where that red peak is and see where the fuel is being consumed experimentally. So, and we also saw in the simulations that the pressures were high. And so what that means is that an optical axis engine that would be used to study this phenomenon would have to be able to operate at high pressure. And the problem with that is that most optical engines are limited to a pressure of about 60 bar, which was significantly lower than pressures that we would expect to see when we auto-ignite power-dense mixtures, and even further when we expect pressures higher than the constant volume pressure. So a Bowditch engine has an extended piston with a slot in the middle of it and a window at the top. And so what this allows is for a 45-degree mirror to be mounted in a stationary location, and then the motion of the piston can go around that stationary mirror, and the camera can be mounted outside to look off the reflection of the mirror up through a window and into the combustion chamber. But the traditional slider crank mechanism for engine reciprocating motion is preserved. So the goals for this type of experiment, for any optical axis engine, the combustion chamber needs to be oil-free, because oil will foul optical surfaces and make the windows not transparent anymore. And the Bowditch piston also needs to be robust enough for the pressure, the intended design pressure. That's often the limiting component, because it needs to have that void for the mirror to be mounted and be held up on these two sides. So the capability that's unique to the experiment that I designed is that it can operate at high pressure. So the design pressure was 250 bar for the experiment, whereas, as I said, typically these engines are limited to a 60 bar limit of peak pressure. I've also designed the engine so that it has a mirrored combustion chamber surface opposite the window, which will allow for Schlieren imaging and the visualization of those density gradients. And a final sort of overarching goal was to make a flexible engine research platform that could be used to study all different types of combustion phenomena that occur at high pressure and high power density mixtures. So full load diesel operation and other things that we haven't been able to look at previously will be possible in this experiment. So for me, the starting point is an optical access engine that we purchased a few years ago that has a 60 bar limit and did not have Schlieren capability. And so for me, from the onset, I needed to analyze all those components structurally and redesign what was necessary to achieve the goals of Schlieren capable and high pressure. So here are some of the components of the engine. The cylinder head here comprises the top surface of the combustion chamber, and this is something that I designed. This adapter plate comprises the cylinder walls, and that's also something that I designed. The remainder of the outer structure of the engine is original to the 60 bar limited engine. There's a bout-edge extension to accommodate the taller piston and crankcase. And then on the right, we see the reciprocating components of the engine, the extended bout piston, and then wrist pin connecting rod and crankshaft. And if you're having trouble visualizing this, I actually have a video of it. A cutaway made by Mark Donahue, who's in the audience among us. So we can see as the piston motion goes up and down, we can stand here and look off of the mirror up through the window and see the underside of the cylinder head. So make sure you give Mark a pat on the back. All right, so to analyze the structure of this under the stresses that would be imposed under 250 bar, you can imagine, so here's a cutaway of the engine, and here is the region that would be experiencing the high cylinder pressure. So 250 bar on an 82 millimeter cylinder bore has a resultant force of about 30,000 pounds, which is about 12 times the curb weight of my car. So these components needed to be robust and then also function as optical components. So the first thing that I determined was that all of these blue components here that are made of cast iron would not survive the tensile loading imparted by 250 bar cylinder pressure. But cast iron is a brittle material and it's excellent at bearing load under compression. And so what I did is I introduced steel beams and threaded rod that can be tightened down to preload the entire assembly in compression. So the steel rods are bearing the load in tension, which is what they're excellent at, and the cast iron is bearing load in compression, which is what it's excellent at. And so then even under high cylinder pressures, the cast iron will be loaded in the compressive region. The cylinder head had to be designed to function as a cylinder head and then also have the optical capabilities that we wanted. So it had to have a realistic exhaust valve area. We wanted the breathing behavior of the engine to be realistic, but we can boost the intake with a high pressure air supply. So we weren't as concerned about intake valve area. And since we were area limited by needing to have a flat head that could be polished into a mirror, we had room for 3 valves, so we prioritized exhaust valve area. This is a view of the underside of the cylinder head. We have a centralized port that can accommodate a diesel injector or an injector to inject water, for example, a pressure transducer, and a spark plug. And there are 2 additional transducers in each side of the adapter plate so that we can get multiple pressure traces. If there are waves traveling, then we can corroborate when they arrive with the images that we get. And so for me, the thing that was most unique about this cylinder head is the mirror polished surface. So conventional mirror materials like glass or plastic wouldn't survive the temperatures and pressures that we're expecting to impart on this surface. But we knew of a company that made metal mirrors, and so we thought we could ask them to put a mirror polished surface on a structural component if we sent it to them. So the cylinder head was designed from 304 stainless steel, which could accomplish a very fine surface finish once we sent it for a polishing operation. And so we manufactured the cylinder head, assembled it with the valves, and then sent it as an assembly to have that mirror polish surface applied to it. So the bowditch had to be redesigned for high pressure, and it needed to be analyzed under static loading as well as inertial loading during the reciprocating piston motion. And so the components we see, there's a sapphire window seated between soft annealed copper seats, and those serve the dual purpose of sealing and also preventing any stress concentrations in the sapphire. And the sapphire is contained in this titanium enclosure, and those components are threaded together and tightened down to preload the sapphire in compression, because sapphire is also a brittle material. And if that has a preload, it'll be better able to bear the load of the high cylinder pressure. And finally, we have the lower bowditch section. And what I want to point out about that is that the wall thickness here was the limiting factor determining the maximum diameter of optical area that we would have. So this is a sketch looking up through the window, and this gray circle here indicates the boundary of the optical area that we'd be able to see. So here are some photographs of the sapphire window sitting on its annealed copper seats and its titanium enclosure. And here is the bowditch piston assembled. And in place of the sapphire window for initial testing, we used metal blanks that were the same size and shape and weight that could let us test things before we introduced the sapphire, because it's expensive. Because Professor Edwards advised me to do that.
Because it's expensive.
So here is a photograph of the completed engine, and you can see it has, I got to choose the color of the big steel beams, gray green. And so here are the rods tying down, and there are nuts here to compress that whole assembly down to preload it. You can see things like coolant hoses and other things that are necessary, but not that interesting. And here's another cross section of the assembly with the mirror mounted here. So now I'll talk about actually operating and demonstrating the engine. The first tests that I did were to test dry piston rings. So as I said, we can't have any oil around the combustion chamber because it'll foul the optical surfaces. But conventional engines use oil for lubrication and for sealing the piston rings. So we used this rings made out of this bronze Teflon sintered material, and they're able to seal around the piston and also glide up and down in the cylinder. So I tested them with just an aluminum blank through 2 million cycles of motored operation, so no combustion, to see how they would perform and if there would be any degradation over time, and what fraction of the isentropic peak pressure that we expect could we reach experimentally. So there's a photograph of a used ring and a new ring, and then a graph showing an idealized model of engine motoring against data, and we see that they overlap very nicely. So these initial tests gave me confidence that moving forward we could rely on these rings to seal the combustion chamber in the absence of oil. The first demonstration I did with combustion in the engine, the goals were to test the components with the aluminum blank in place under fired conditions, and then also see how the rings performed under combustion conditions. And the first observation upon beginning to fire the engine is that the combustion data and the pressure data we were getting looked as we would have hoped and as we would have expected from the engine. But we learned even more once we took it apart after that first run. So this is a little bit like a joke, but not a joke. The dry rings, they can burn. But so the way that we plan to run the engine is skip firing, so running in a set of 10 cycles and then motoring and then running a few more cycles and motoring. But for these initial tests, we were sort of increasingly aggressive in what we were subjecting the engine to find the limits and just to understand how to not be afraid of what might happen if we went slightly outside the bounds of where we plan to operate. So we can see that when we took the engine apart, the top rings were mostly consumed here, and they also deposited a varnish-like coating on the mirror. And so it's no longer a mirror, but we were able to recondition it. And another thing that was really good about those initial tests is that we learned that the failure mode for the rings is not catastrophic. Even though a lot of them were eroded, the engine continued to behave as we'd expect, and we were able to tell the rings had deteriorated based on the loss of pressure ratio during the operation. And we also found that when we tighten the components together, that titanium enclosure that's threaded together around the window, we didn't tighten that to as tight of a preload as we would need for it to continue to seal over the temperature range. So we needed a revised assembly procedure for that before introducing the sapphire window. So for a second demonstration, there was a revised procedure for torquing those components together to a high torque to have a high preload on the seats. And you see the combustion data from the engine looked very similar to what we saw at the beginning. It's compression and expansion and work being the area here. And this is contrasting a motored cycle to a firing cycle. And the same data you can see on a log plot of pressure volume. And the reason we would look at this on a log plot is because we want to see straight lines indicating isentropic compression. And this down here is very exaggerated by the log scale. You see that actually these fluctuations are small in terms of their actual value. So finally, we determined that it was time to introduce the sapphire to the design. And so you can see on the left a photograph of the view we saw before with the animation standing outside the engine, looking at a reflection off the mirror up through the window. And here we can show the sapphire before it went. Don't worry, fear not. And
Was that a crack propagating across? No.
Still in one piece. And so we can see there's the spark is at the top, and the flame front we can see propagating down. We can even see some of the fluid motion. So here are the images as panels, and when they're viewed as stills, you can actually see the flame front better. So we ran at the operating point I just showed, and then also at a boosted operating point to run the engine at high pressure. So we reached a pressure of just over 100 bar with spark ignited operation for the engine to demonstrate high load combustion capability and the ability to capture images and data under those operating points. And just a quick note, we don't have the laser to do the Schlieren imaging, but there's a Schlieren capable experiment, and a future student will do that. So now I'd like to just conclude by summing up really briefly. The quasi-one-dimensional reacting compressible flow model effectively captures the gas dynamic coupling and impedance, and can be used to explore different cases where the coupling occurs and where it doesn't, such as uniform dilution or temperature gradients, etc. The optical axis engine is capable of 250 bar pressure with a Schleyer imaging capability by having a mirror polished combustion chamber surface. And the experiments demonstrated engine operation under high load combustion conditions. And so the engine platform that was developed in this research will be useful for optical studies of high power density, high efficiency combustion strategies. Sure. I need to acknowledge my funding sources. Thanks to Bosch and the Department of Energy and the National Science Foundation for sponsoring my work and me. I need to thank my defense committee for being here today, my chair, Adam Grant, my leaders, Professor Laley and Professor Mitchell, Professor Gerdes, and my advisor, Ms. Edwards. Thank you for caring about me as a person, and not just as a source of cheap labor.
Which one of us are you referring to?
Yeah, there's horror stories that you hear about grad school, but I didn't experience any of them. And I feel honored to have gotten to work during the last 6 years. And the project that you run to work on is mechanical. None of this work gets done with only these two hands. I had help from lab techs and machinists at Stanford. Lockbeard Joe Hall is a wizard at machining. He can make anything. Scott Sutton was our lab tech for a few years at the start of my PhD. And you can see here one way that he would tend to solve problems. The other way is hit it with a hammer. Actually, I learned so much from Scott about the practical, more nitty-gritty aspects of building an engine. And Bill Sabal is another machinist on campus that was very helpful. So also, I didn't manufacture all the parts with my own two hands. There were a lot of area machine shops who went outside of their typical wheelhouse and comfort zone and what they typically produce, and were willing to talk to me and not think that I was crazy. Maybe initially they thought it, but then after a few conversations, oh, why are you doing that? Okay, yeah, we can do that, but why? And so, yeah, there are some very talented machinists and welders in the area. And I also need to acknowledge some of my sustenance sources. At Cardinal Sushi, they say, "Hey, Julie, the usual, how's the engine?" So they know. And my blue bottle this morning. Yeah, Starbucks and the Axis Palm, and Cardinal Sushi and Blue Bottle are closed. I need to acknowledge some project colleagues. Colleagues from Bosch, a number of you are here. Joelle, Nikhil, Eric, Varun, Dave, and Alex. I learned so much from you guys in the lab, in meetings, especially Joelle. We were in the lab trying to figure out the engine, doing all kinds of ridiculous things, and you were there for some of the rough moments, man. And another sort of unofficial colleague is my friend Alex Main, and we would swap. I would help him with thermodynamics, and he would help me with the numerical model. And he's already off doing a postdoc. I need to acknowledge the best lab colleagues. That is funny. Who made their faces look like my hand. That was Mark. You can see their faces up here. During my first design review for the cylinder head, Mark noticed that it looked like a face. And then after that, the entire meeting was a mess. And I couldn't say anything without people laughing and just taking me seriously anymore. Yeah, so here are pictures of my lab. I especially want to give a shout out to Mark, the corner there. He and I were working on the engine together a lot, and he'll be taking over the experiment. And the night that we got that first combustion video, I think was like Mark's 16th hour of work for the day because he'd been teaching for 9 hours, and so yeah, I wouldn't have gotten that without you. And Adelaide is watching this with me. And then I had 3 undergrads helping me last summer, and they were just like so gung-ho about building things. So Brady is here preparing a rotary engine piston in his natural state. Juan is up there in the other Stanford engineering shirt. And I don't have a picture of Sean. Sorry, Sean. If your picture isn't up here, it doesn't mean I don't love you. But yeah, I just appreciate so much people like Nat keeping my spirits up. Like, that stuff is really rough. I appreciate you guys. Need to acknowledge my friends. Yeah, this is like the part where I try to acknowledge everyone, and it's impossible because there are so many people. Yeah, I had amazing friends to keep me going through this journey. And there's one person I want to especially call out, and that's the girl in the orange helmet. If getting a PhD is like Frodo taking the ring to Mordor, then Mary Litherland was my Samwise Gamgee. Frodo wouldn't have gotten far without Sam. So we were roommates for 4 years, and man, the number of times we both just said, let's quit and go build a homestead in Montana. Yeah, I wouldn't be here today without Mary. I need to acknowledge my church community and Reformed University Fellowship. David Jones, don't hide your face. You're right here. This is my pastor. Before I came to Stanford, I knew I was coming here for a whole year before I got here, and that whole year I was really praying about who my friends would be and what kind of community and church I could find, because I knew I wouldn't make it through without that kind of support. And like I was not prepared for like how wonderful the community that I found here was. And so, yeah, you guys shaped my Stanford experience, and a lot of you have t-shirts with my face on them. I want to borrow something that my friend Steve said during his acknowledgments and say, you guys only had to listen to me for 45 minutes. You still have to listen to me all the time. So I need to acknowledge my family. My brother Mark is here, my mom, Anne, and my Aunt Barb, and a number of other family members that couldn't be here. There are actually too many of them to fit on this slide, which is way too many. Yeah, I mean, they raised me and made me who I am. And I was once this little. This is my mom when she had different hair.
Hey, Mom.
So at this time, I would like to take your questions. Mom helped me in these labs. Yeah, the fire extinguisher.
So you had to increase the preload to the sapphire window?
Yes.
How exactly did you accomplish that?
I'm glad you asked. You didn't even give my brother the chance to ask the question I planted. To apply such a high torque, I built a torquing apparatus. So I built these hexagonal pallets that could grip the two halves of piston that needed to be tightened together. And then the bottom one fit into this base, and then the top one fit into an impact socket that's about this big. And then, weighs 20 pounds. And then a torque multiplier was used, so we could input torque, and then 18.5 times that torque was delivered at the output of the torque multiplier.
How big is the multiplier? Was it like you bracing all your weight and pushing it on the floor, or is it like
So this base transfers the reaction force like through to the bottom, and then we were able to pull using a torque wrench up to 180, whatever this divided by 18.5 is. What we applied to the input, and I think I asked Mark or somebody to do that last little bit of work.
Not small.
Great.
So, with regards to your really beautiful images you got, you see the flame front pass through the chamber, but then afterwards it's still pretty well illuminated.
Mm-hmm.
So I'm curious what's illuminating the chamber at that point?
That's a good question. So in some of the other images, there was some evidence of ring material that was burning. And then also the engine has fairly large crevices above the piston rings. And so as the piston started to move down, that could have been beginning to ignite around the edges where we couldn't necessarily see. And in some of the runs, we can see sort of like some of the flames creep back in, and they're tinged green a little bit, indicating some comfort. Yes.
Actually, two questions. One, you used the GRI mechanism, but
Yes.
that was never tested above basically atmospheric pressures. Do you think your calculations were all sensitive to the mechanism, were strongly sensitive to the mechanism?
I think, yeah, I mean, the answer is yes, but the purpose of the model isn't to predict exactly what we would expect to see. It's more intended to capture the effect of different factors. So a lot of the models in the literature that are similar to this have a one-step heat addition, and they don't capture the effect of kinetics at all. And so what I wanted to do was incorporate the ability to have moderating species and segregating chemical species and capture that effect. But I don't expect for the values to be predictive.
And the second question was, when you showed the example where the pressure wave outran the flame front, that it wasn't until after the reflection that the wave, well then, wouldn't you be tempted to say, well then, can I just get a pressure wave that just barely outruns the chemical wave, and so that they hit the wall at the same time, or almost the same time, and there's no...
Right. Yeah, so that would be possible. It would be difficult. Yeah, too difficult probably. But the purpose of that example, beyond showing like, okay, the decoupling can happen initially, is that if we imagine that that had been instead some other reacting region pushing a pressure wave, that even if the pressure wave from this combustion hadn't made it, another pressure wave could have arrived and caused the coupling.
Yeah. How quickly is that mirrored top surface foul up, and then is that prohibited to keeping data? And then also with rings, like when you use pressure there, how quickly does that happen?
Yeah, so the mirror surface, I guess, so the fuel that I was using in the images is propane, and propane will tend to want to stay in the gas phase, whereas something like gasoline or diesel might want to condense on a surface. So I think the duration of firing that you could do, or sort of like the total number of cycles, would depend on the fuel that you were using. We did notice by the end of probably about 1,000 combustion cycles, not consecutive, that the window started to have a few little deposits on it, but we could still see through it. And so I imagine that you'd be able to get plenty of data before. And then as for the rings, with skip firing, they should last a long time. The cycles that I ran through just motoring was like 12 hours. And so there's actually like a pretty good amount of time you could go between needing to change things out. And there's a good chance that you would need to clean mirrors or windows before you would need to change rings. Okay.
So for the future experiments with the Schlerin, what are the changes to the experimental setup that are coming up?
So one would be having the light source to do the Schlerin imaging, the laser. And another is that right now the compression ratio of the engine is a little bit too low to get HCCI combustion in like a steadily propagating mode. And so there are shims in the engine right here and right here. And just by swapping out different shims, we can adjust the compression ratio by adjusting the clearance height at fountain center. And so I would make another set of shims that would let it to go in like a 13-to-1 compression ratio or so. Okay.
Does the laser that you would use for Schlerin, does it just use the same optical path? Like you shoot it in the side and it goes up and then reflects off? Okay.
Yeah. Yeah, and that would be captured with the blue, or well, blue or green, depending on which color laser we got. But that channel of the camera would pick up the Schlerin, I think, and the other two would still pick up the luminosity.
One more.
Okay, that.
So from a layman's perspective, because I understand very little of this, but understand kind of the overall how an engine works. How do you take an engine that big as a prototype and then for future use in cars and make a smaller engine out of what you've designed here? Or is that even feasible?
Well, so what I've designed here is intended for research, and it includes things like hydraulically actuated valves and all kinds of things that you wouldn't actually build in a production engine. But by having the experimental flexibility to understand the details of the combustion process, you could then go and design a better production engine from what you've learned here.
So do you imagine someday there will be an engine like this?
There could be an engine running.
Not like
right.
this, but in a smaller version.
There would be engines running combustion strategies that were investigated and sort of vetted and studied using this type of apparatus.
So it could be turned into a smaller engine.
Sure. Yeah. Yes.
Thank you.
All right.
All right. Thanks, everyone.
We have about a 5-minute break, then we'll go to the closed portion. Food outside.